Alright guys, let's see if I can make some sense of this derivative stuff for you from the Chapter 10 pretest, getting you ready for your quiz on Monday. So the first, I think I left off with, oh, did I lose? Darn, I think I lost a bunch of stuff that I did. Drat. All the derivatives were on here and they got lost in the shuffle. How about that for fun? Anyhow, we'll start with that back page with the area underneath the RAM stuff. And if you look at it, this is left rectangle approximation method, and then I've graphed out the 2 times quantity x minus 3 squared. That's a parabola shifted right 3, and then instead of going over 1 up 1, we go over 1 up 2. Over 1, instead of over 2 up 4, it's over 2 up 8. You're doubling your heights, so you're seeing that graph right there. But we're going to do area of left rectangles, using 8 of them from 0 to 4. So that means we're going to have to squeeze them in there really tight. So I have the ability to zoom in on this technology. For you guys, it's a little hard to draw it in there. You might, I don't know if you maybe doubled the size of everything just to make it doable, but that means my rectangles are little slivers, half widths that go across there. You can even hardly see what I've got written in there, but that's just to give you the idea, and they touch on the left-hand side. So because they touch on the left-hand side, that over approximation on the left is kind of evident, and then there's an under approximation on the right. Altogether, the calculation is the width times all the heights. And the width is whatever your domain is, 0 to 4 in this case, so a width of 4, that's your domain. And divided by the number of rectangles, so 8 rectangles, there'll be a half a unit each. So now the heights are f of 0, f with 0.5 plugged in. It starts on the very leftmost lower bound because of left rectangles, and it ends, the very last height is f of 3.5. because you always stop one width less than the domain that you have. So one below the upper bound, in this case 4. So we want to stop one width less than 4, which is 3.5. So we plug in all those values, and we get our output a half times all those plugged in. Right now I'm going to give you just the setup for that, and then let you go ahead and do the calculations on that. Let me know if you have other questions. In class, if we have time, I'll show you how to use lists to make that a lot easier. Alright, next one, same thing on number 12, but we have a line, and I hope you're enjoying Ethan piping in the background there. We're going to do right rectangles, so they touch on the right. Thankfully, there's only 5 of them, and so that's a width of 1 per rectangle. So, and then the height, you start with 1 width from the lower bound, and you end on the upper bound, since you're wanting to touch on the right-hand side. So here goes. We get the calculation. Just plug those numbers into the function itself, get those heights, and you're good to go. Number 13, you want to draw the picture, and then with this, remember, this is a mathematical expression for, give me the area under x plus 4 from 3 to 8. So the width is 3 to 8, that distance there, that 5, and then the height is that function x plus 4. So your roof function is x plus 4. All you do is you actually make that into, since it's a geometric shape, you can do a trapezoid, which is what I chose to do. I got a heights of 12 and 7 for each of those ends. Those are our base 1 and base 2 heights for the trapezoid, and our width, which we actually call our height in this case. It's kind of weird. You know how trapezoids are usually on their side. 5 would be the height of a trapezoid, and 7 and 12 would be the base 1 and base 2 respectively. And so I've got this expression here for area of a trapezoid, and you get 47.5 units squared. Alright, now I'm going to make another video for the derivatives. I went through and did all that work. I don't know where they went, so maybe I'll just look it up somewhere. But alright, get back to you.